Today's lesson is on section 8.4, using scientific notation. We're going to, again, this chapter 8, we've been doing a lot with exponents and exponent rules, way to simplify problems with powers. Scientific notation also have powers involved in them when we write a number in scientific notation. And we're going to learn some ways we can actually use the rules we've learned so far in this chapter with numbers that are in scientific notation. Just as a quick reminder, here are the rules that we did cover already, and if you need help or kind of review on those, and maybe check out some previous lessons as well. Remember, we've learned all these six different rules. Like the very first one, if I'm multiplying two powers together and they have the same base, I add the exponents. Or if I have a power to a power, I multiply the exponents. Or if I'm dividing two powers that have the same base, I subtract. So just kind of remember some of those powers we've used so far in the past. Those will come up again. Actually, those are things we can use here in this section as well, as we'll find out. And using those rules, we can simplify problems that have scientific notation. First, just a little reminder of what does scientific notation look like. Right now on the board, I've got a bunch of different numbers, 10 different numbers, and I'll ask the class which of these numbers are actually in scientific notation. Some of them look close to scientific notation. Some of them, as I'm going to call them, are kind of imposters. They look close to what it's supposed to be, but they're not exactly it. And if we look at these carefully, and I'll have students kind of pick some out, and usually they can pick out some of the good ones and some of the bad ones, and some we're not sure about, but we usually can figure out that this right here, 1.8 to the 7th power, is just some kind of power, so that's not scientific notation. This one also here, people will usually be able to figure out after a little bit if they're looking at all of them. 7.05 times 10 to the 8th, or times 8 to the 2nd power. That one also, because it's times 10 to the 8th, that one also is not going to be scientific notation. Some of these other ones are looking a little more closer to what scientific notation could be, but as we'll talk about, and usually after we pinpoint it a little bit here, we'll realize that numbers, there's only 3 numbers up here that are scientific notation. It's this one, and this one. Those 3. As you look at the other ones, you may wonder yourself too, if you're still kind of thinking like, oh, which ones are scientific notation? You may wonder why some of these other ones are not. And we'll talk about that here on the next page too, like the definition of what scientific notation looks like. But why is this a little different than this? Well, you notice this has 91.12 times 10 to the 3rd, whereas this is just 3.49 times 10 to the 5th. What has to happen for scientific notation is we can only have one number to the left of the decimal when we rewrite something in scientific notation. And even this one, this is like the decimal would be right next to it, so this would be 4.0, you could say, times 10 to the 23rd. All these other ones, if it has 2 numbers, that doesn't work. That's not quite scientific notation. Same thing for this one, 124.1. That's 3 numbers to the left of the decimal. 100.5, that one's not quite it either. And these that have a 0 in front, 0 isn't a digit we consider one that's significant, so the one that would be in front of the decimal for making scientific notation. So even these numbers right here are not going to be scientific notation. They look pretty close, but they are not it. Just these 3 are numbers that are in scientific notation. And so if you're taking notes along with me, here's kind of just a general guideline. What should it look like when a number is in scientific notation? It should look like this. C stands for some number, some constant. Some number times 10 to the nth power. And that number C needs to be at least 1 or greater or less than 10. So like 9.9 could even be about as high as you can go. So here's some examples of some numbers that you could have for scientific notation. You could have something like 2.5 times 10 to the 8th power, or 3.7 times 10 to the 20th power, or 9.2 times 10 to the negative 5th power. And we can also have a negative exponent, as we learned how to deal with already in this chapter. So these are numbers that would be in scientific notation. Just 1 digit to the left of the decimal times 10 to some power. Again, because there's a power in there, because there's an exponent involved, we'll find out some rules there's some of those old rules we learned already in this chapter we can use too when we're using numbers with scientific notation. Some of the first problems will just ask us write a number in standard notation. Some of the problems we'll see today. Standard notation just means writing the number out as you would normally see it. So not in scientific notation, but just written out with all as it should look. Maybe even if it has a lot of zeros after some of the significant numbers or whatever it may be. Looking at maybe this first one here, just to kind of give you an example of what that means. So this first one, 2.5 times 10 to the 8th power. Well, again, what does it mean 2.5 times 10 to the 8th. Well, 10 to the 8th, that means it's like multiplying by 10 8 different times. We're taking this number times 10 8 different times. And as I'll remind the class, a little trick maybe you've learned in the past, I'm just going to move some things around here to give myself some more room. Maybe a trick you learned in the past. Remember, if you want to multiply a number by 10, like let's say the number 16. I want to multiply that by 10. Well, what happens is I just add a 0 to the end of it, so I'm just going to get 160 if I multiply it by 10. If I take 160 times 10, I'm just going to add another 0, so 1,600. So whenever I multiply a number by 10, anytime that happens, it's just like adding a 0 on the end. Or if it's a decimal number, well, then it's just like moving the decimal one spot to the right. So let's say I have a number like 82, like 82.15, and I'm going to multiply that by 10. Okay, again, maybe a trick that you've learned in the past. Anytime I'm multiplying by 10, it's just like taking this decimal point and sliding it one spot to the right. So 82.15 becomes times 10 gives me 821.5. Anytime I multiply a number by 10, it's just like moving the decimal spot one place to the right. So go back to that problem there that I made for an example, 2.5 times 10 to the 8th. If I'm multiplying this times this 2.5, this decimal, times 10 8 different times, that's the way I can think about it, well then it's like saying 2.5, well, times 10 once would be moving the decimal spot one more time. And I have to do it 7 more times, right? So that would make 7 zeros after that. 1, 2, 3, 4, 5, 6, 7. So I have 7 zeros then after my number. So really, my answer would be 25, and then 7 zeros after that. And I can put my commas in after I've made my number. This is really like 250 million. So that's how I can write a number in standard notation. That's what it would look like. So we'll look at a few examples to do that, so a little bit of practice. And again, I think scientific notation is something that by 8th grade we probably have seen before, but a little bit of review so we don't go into the new stuff without remembering this prior knowledge here. 5.9 times 10 to the 12th. So this one, again, 5.9 times 10, 12 different times is what's going to happen. So it's going to be like moving that decimal 12 times to the right. And as I'll remind students, that doesn't mean, though, you put 12 zeros at the end, especially not for this one, because I have to move the decimal one spot over just to get past the 9 there, and then I still have to move it 11 more times. So sometimes you can kind of figure out the math that way. It's like, well, I'm going to move it one time, and then 11 more, so it's like 59 with 11 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I can put my commas in as I kind of backtrack here. But that's what I get for a number. Let's see, thousands, millions, billions, trillions. 5,900,000,000,000 is what I get for a number for that one. Okay, I'm going to go down to number 2 here. I haven't unveiled that one yet, but number 2, I can just practice in a few of these. This one, 8.2103 times 10 to the 3rd. So again, I'm going to take this number and times it by 10 3 different times. That's what that's saying. Well, that's going to move the decimal 3 different spots. So I'm really just going to get 8,210.3. I won't even get to the end of the number. So again, just realize, yeah, it doesn't, when you have something times 10 to some power, doesn't mean just throw a bunch of zeros on the end, or however many zeros this says. I have to move the decimal over however many times it tells me so. In this case, I didn't even get to the end of that number, 8,210. If it's a number in scientific notation that has a negative exponent, what really is happening there, I can go to some of the math behind it, but just kind of realize one way I tell students to think about this is it's like a very small number instead. Kind of what's happening here, you could think 1 over, this is like if I think we just worked with negative exponents, right? I could think of this being like 1 over 10 to the 4th. So that's what this number is getting multiplied by. And so what ends up happening is kind of like it's getting divided by 10 4 different times. Okay. Well, if we're multiplying by 10, like we're over here, then it moves the decimal to the right. If we're dividing by 10, which is really going to happen here 4 different times, it's like moving the decimal to the left. So that's what's going to make it a very, very small number in this case instead. So if I'm going to move the decimal 4 spots to the left because it's -4, well, what's going to happen here? I'm going to have 4, 7, 8. Here's where the decimal started. I'm going to put 4 spots. 1 to get past the 4, and then 3 more times. So I'm going to fill in zeros there. So I'm going to have 0. Okay, my numbers ran together. They're my 2 answers, but 0.000478. Same thing with that next one. It's times 10 to the negative 8 power. So again, I'll tell students, well, if it's to a negative power, you can think of it. Oh, that means it's like a really small number. So that means I'm going to move the decimal to the left. So I'm going to move it once to get past the 1, and then 7 more times. So I'm going to end up with 7 zeros. And then 12307, whatever that number ended up being. So that's us writing a number out in standard form. Now, if I want to go backwards from that, some of the problems that they'll say write the answer in scientific notation. So now I want to make it in that form like we talked about from the first page here. Just going back to that for a second. I want to write it so it looks like this. Again, I got some number where, or even going back to farther to my first page. Remember, I only want one number to the left of the decimal like we talked about, and then times 10 to some power. So if I'm going to go back to the examples here now, if I want to write these problems in scientific notation, well, again, remember, we want only one number to the left of the decimal. What I'll tell students to usually do then is focus on that decimal part first and think, okay, looking at this number, where would the decimal have to be so that this number would be in scientific notation? Well, it'd have to be right here between the 4 and the 5. So I'm going to write 4.502, and then once I get past this 2, it's all zeros after that, so I don't need to include any of those zeros in my number. I just include the significant figures, or significant digits. So 4.502 times 10 to some power. And what I'll say is, here's where our decimal usually is. So how many times did I have to move it to get to this place that I wanted to put it in between the 4 and the 5? Well, I had to move it 1, 2, 3, 4, 5, 6, 7 times. So that will make it times 10 to the 7th power. If I went backwards, I'd end up moving the decimal 7 times to the right, and that would give me this original number. I'm going to skip over to number 3 because that one's similar to the one I just did, but just kind of, I'm going to show one of those as well. Or should I show one of these again before I move on to the other ones? So this number right here I want to put in scientific notation. So where would the decimal have to go? Well, I want to write it so there's just one digit to the left of the decimal. So I put it in between the 1 and the 4 right there. So this would be 1.487242, and I guess I don't actually put that last 0 on there, but I got to put all those other numbers that are significant. So all of that times 10 to the, well, what power are we talking about here? Well, again, how many times did I have to move the decimal to get it to the spot that I placed it in, between the 1 and the 4? Well, again, this one also had to move 7 times. So 1.487242 times 10 to the 7th power. Looking at number 3 and 4 here, again, these have the really small numbers instead, like 0.0045, some kind of decimal, some above 0, but very small number. So it's going to be the same kind of process. I want to move the decimal right here between the 4 and the 5. So I'm still going to write 4.5 times 10 to some power. But again, if it's a very small number, well, I actually end up moving the decimal backwards to get to the 4.5, right? I moved it to the right to get here. So in this case, it's, well, how many times did I move it? 1, 2, 3 times. So it's to the negative third power because it's a small number. If it was positive third, you know, if this said 4.5 times 10 to the positive third power, well, that number would actually be what? 45 with 2 zeros after, that'd be 4,500. So the fact that it's a negative exponent, that tells me it's one of those smaller numbers, less than 1. And so that's how I'd write that, 4.5 times 10 to the negative third power. Same thing with number 4 here. I want the decimal to go right there in front of the 2, or I should say right behind the 2. So I have to move it in this case also 3 times. I've got all these significant figures after it. 2.0302 times 10 to the negative third. So that's how we write a number in scientific notation. I'd say first concentrate on the part with the decimal. See where am I supposed to place that? Where would that end up so that this number would be in scientific notation? And then I'll concentrate on what power it would have to be to, times 10 to the what power. Well, again, a lot of that was hopefully kind of a review of scientific notation, but now getting into what we'll actually use those exponent rules in this chapter, how we'll use those with scientific notation. I'll look at just a couple of these examples here and give you an idea what can happen. So these problems say evaluate and write the answer in scientific notation. Well, now this first one, we're taking 2 numbers in scientific notation and multiplying them together. Now you could use your calculator for this, but as you'll find out in the MCAs and so maybe even tests in my class, we might not be able to use our calculator. So just like with the exponent rules, I want you to be able to simplify something like this without having to jump right to your calculator for help. What I'll remind you, or what I'll show you though, is again, we learned some of these exponent rules early in the chapter. So a problem like this is actually very similar to a problem like this. And I'll kind of show you what I mean. Even though they don't look so similar, I'll show you that they actually are. In this problem down here, which we've done, I've got some number here multiplied by, well, some kind of power, right? And then that's times some number multiplied by a power. We'll look at the problem I have up here now, the one with scientific notation. Isn't this actually the same kind of setup, even though I don't have variables in there? I have some number times something to a power, and some number times something to a power. So really notice that these two problems are very similar. I just have different bases here, but I still have powers, but a different base. One has a base of 10, one has a base where it's like a variable like x. And then I have numbers like coefficients that are multiplied to each one of those. But really these problems, if you look at them carefully, they're very similar problems. We'll think about how we did a problem like this below. In a problem like this, where the first term is multiplied by the second term, I can just multiply these two numbers together, the coefficients, and get 6. And then we know a rule for the powers. I can add the exponents and get x to the 7th. Well, what do you know? The same exact thing I can do with scientific notation. So on problems like these, what I ask you to do is multiply 1.1 times 1.5. And if you want to use your calculator a little bit there to help you, I'm okay with that. But I don't want you to punch the whole thing in because it's not going to help you in the future learn how to do problems like this. But you could punch these in and get 1.1 times 1.5. And I think in this case, I think that ends up being, I'm going to punch it in myself here. 1.1 times 1.5, I think it's 1.65, yep. So that gives me 1.65. And then I can combine these powers by adding the exponents. It's 10 to the 9th power. So there's that answer still in scientific notation. But now I've combined those two. I can multiply those two numbers together that are in scientific notation. And my answer is still in scientific notation without punching all those zeros in or all the big numbers in. So there's a way to do that using those exponent rules we learned before. Well, now I've got one more example. And this one, as you can see, is dividing two numbers in scientific notation. What do you know? I've got one that kind of hints and shows us, oh, it's something we've done in the past already. Remember a problem like this where I'm dividing 15y to the 4th and 3y squared. I can just divide these two numbers, the coefficients. 15 divided by 3 gives me 5. And I can subtract the two exponents here and get y squared. Remember we did rules like that. Well, what do you know? The same thing can happen up here. I can divide these two numbers and then subtract the exponents for that power and keep it as 10 to the whatever power that simplifies to. So 6.0 times, or divided by 1.5, I think ends up being 4 right on the nose. And all of that times, well, 12 minus 3 gives me 10 to the 9th power. So we learned some rules earlier in this chapter, but with exponent rules. There's some rules for simplifying exponents. And now in this section, they're showing us that even in scientific notation, the problems are actually very similar to things we've done in the past. And we can use those rules to simplify these problems too in scientific notation. There's ways we can simplify these using what we've already learned in this chapter.